Hello, AP Calculus BC, and welcome to your last lesson or set of lessons for the entire BC curriculum. Super exciting, right? You guys are done at the end of a 2-year journey. Of course, we still have to go back through and do plenty of review, and there'll be some videos on that. But really, at this point in time, or by the end of these next 2 videos, you should have learned everything you need to know to be super successful on that BC exam. Speaking of 2 videos, I am going to split this lesson over 2 different days in 2 different videos. The first video is going to cover probably just day 88, and is really going to be our introduction into logistic differential equations. And then day 89 is going to take you guys through some more concrete example problems. I found putting it together is just way too long and overwhelming. I'd teach it over 2 days, so why not make 2 different videos? Yeah, I think we should probably get to it. I actually really like this opener problem quite a bit, so let's tackle it. We're coming off of being able to solve differential equations, and this is a differential equation that we're going to be able to solve. So here we go. A certain rumor, makes me think of Umbrella Academy, popular right now, you heard a rumor, spreads through a community, or maybe a high school if it's a rumor, flying through like wildfire, at the rate given by the differential equation below, where y is our output and is the proportion of the population that has heard the rumor at any time t, right? Remembering proportions are like percentages but as decimals, so if 0.4 of the population has heard that, then that means 40% of the population has heard it, right? So it makes sense that y has to be less than 1 here, right? Because at 1, it would be 100% of the population has heard the rumor. If at time t equals 0, 10%, or as a proportion, 0.1 of the population have heard the rumor, find y as a function of t, right? So we're trying to solve, so we get y as a function of t. All right, well, let's get to it. We're going to probably need 3 columns here, but having seen this problem once or twice before, I'm actually only going to do maybe 1 column to start. And you're going to definitely want to write a little bit small here. And then I think this second column, we don't even need all of it. I'm probably going to need some space down below. So I think we're going to do this, and I may have to erase, so I apologize. But let's get to it. You guys should be able to at least get us started, right? We know that dy dt is equal to 2y times 1 minus y, and our first step for any separable differential equation is to move all of our variables, all of our like variables to each different side. I'm going to leave the 2 on the right side just so dt has something to hang out with, otherwise it feels a little lonely, and we'll move the y and the 1 minus y through division to the other side, right? Something like this, the dy, and then we have 2 dt. We'll sneak our little integral symbol in here, and we're looking pretty good. Well, until we start to take our antiderivative. The antiderivative of the right side isn't bad. That's just our 2t plus c. But the left side is a little bit tricky. In particular, we see this multiplication down here, which means we need to rewrite this somehow so that there's no multiplication. You might say, oh, can't I distribute the y? And you can. But then, I'm going to erase this, you're going to end up with negative y squared plus y, and we don't know how to take the antiderivative of that. You could bring it up, but then it's to the negative first power, which is usually natural log, but it's not natural log. If you have an extra square or not something to the first power, U substitution won't work. In fact, we might be starting to panic if we saw this on an actual AP exam, until you remember all the way back to literally our first set of lessons, the first or second week of school. And you might remember that if we have a fraction with 2 factors in the denominator, we can actually break apart, or maybe even we call it decompose this fraction into 2 smaller fractions. Let's take a look. Right, this is a nice reminder for you before we jump into review. We can rewrite 1 over y times 1 minus y as 2 different fractions, a over the first factor plus b over the second factor. We need to multiply by, or give everything a common denominator to start canceling things out, right? If we give everything a common denominator, that gives us 1 equals a times 1 minus y plus b times y. And then we just carefully pick our values of y to cancel out various factors here. So for example, I'll cancel out the first one by picking y equal to 1. That gives me 1 equals, this is 0, so that's gone, plus b times 1. I think 1 equals 1b means that b equals 1. Do the same thing to cancel out b. Let's see what happens when y is 0. Right, this becomes, that's an a. 1 minus 0 is 1, and then b times 0 cancels, and I think we find a is 1 as well. What a nice decomposition. Now that we've seen what this looks like decomposed, we can go back and tackle this problem a second time. But instead of writing what was over here before, now we're going to use our decomposition, and we're going to say, let's find the antiderivative of a was 1, doesn't really matter because they're both 1 over y plus 1 over 1 minus y dy equals the integral of 2 dt. Now we're getting somewhere. Let's do some antiderivatives. Antiderivative of 1 divided by y, natural log absolute value. And our other one, we need to be careful here. It is 1 minus y, but we need an extra negative to account for the derivative of negative y. So we'll just throw that one in there. Equals 2t plus c. And just to condense this a little bit more, a little less writing, realize that when we're subtracting logs, we can write that as a quotient of the first divided by the second. And now I think we're in business. All right, well, let's use that guy and also the initial condition, which it tells us at an input of 0, time of 0, we know it's 0.1. And let's use that to go through and solve for the constant here. 0.1 divided by 1 minus 0.1 equals 2 times 0 plus c. Nothing bad. You guys should be able to work through that one. Natural log 0.1 is 1/10, and then 1 minus 0.1 is 0.9, or 1, no, not 1/9, 9/10. There we go. And I'm pretty confident that fraction is going to stay positive, so if you apply the absolute value, it keeps it positive. So we end up, I think, with the natural log multiply 10 over 10 of just 1/9 equals c. And that looks pretty good. Now, if you wanted to be really clever here and save you a little bit of time, and I like this step, we can realize that this natural log of 1/9 is really the natural log of 1 minus the natural log of 9, isn't it? We can break this apart the same way that we brought two logs together. We can split logs apart. And that's useful because I recognize that natural log of 1 is 0. And so we actually just find c is negative natural log of 9. If you substitute this into your calculator, you'll get the same answer as that one. All right, now what? Well, I'm jumping back over here. We have the natural log, and because my initial condition kept the interior positive, this goes back to our branches of differential equations from last class, I'm going to go ahead and just drop the absolute value. No reason to keep it here. Y divided by 1 minus y equals 2t minus the natural log of 9. All right, let's go ahead then and isolate y. Exponentiating each side I think would be good. So e to the 2t minus the natural log of 9. What are we going to do here? Well, that's kind of an ugly exponent, so let's take a quick second and rewrite this as e to the 2t times e to the, and this is kind of weird with this negative here, but that's okay, to the negative natural log of 9. Maybe I should have kept it as 1/9. Awkward, but that's all right, because e can only cancel out natural log, not with the negative. Drat. Did some extra work. Oh well, reminded you of what's going on here, so I'm going to get rid of this and say, well, we already talked about how these are equivalent. Let's just rewrite it there. Yeah, it's going to be better. Those cancel. Y divided by 1 minus y equals 1/9 e to the 2t. Whew. Are we done? No, sadly. We still need to isolate y here, and unfortunately we have y in both the numerator and denominator, so let's multiply through by 1 minus y, right? That's not going to hurt. So we get y equals 1 minus y times 1/9 e to the 2t. And it's looking okay, but now we need to actually get into that y, so we'll have to distribute this guy into both. So y equals 1/9 e to the 2t minus y times 1/9 e to the 2t. Move both the y's to the same side. Yes, we are almost done with this, I promise. And there's good news coming up soon. E to the 2t equals 1/9 e to the 2t. There is a y in common to both of these, so we'll need to factor that guy out. And so this looks like 1 plus 1/9 e to the 2t. And finally, at long last, we have isolated y. 1/9 e to the 2t divided by 1 plus 1/9 e to the 2t. Woo! Go us. And look at all that work. Now, you might be feeling a little apprehensive looking at this going, oh my gosh, dude, Mr. Grant saved this for last because logistic differential equations have an insane amount of work. And actually, no, I'm coming to you with both some good news and maybe some less ideal news for you. So the good news is that you never have to do this on the AP exam. So maybe the bad news is we did all of this and you don't actually have to do it, but it's still good because it reviewed a whole bunch of concepts, right? Partial fraction decomposition, log rules, showed you how to solve for y in a fairly complex equation. Nothing bad there. This format, though, is known as a logistic differential equation, and we are going to really delve deeply into what that means. But I am going to mention that we did just solve this, but you are never going to be ever going to be asked to solve a logistic differential equation. Instead, you're going to be asked various characteristics about the solution, but you never need to go through this whole process. Just as a bonus, because we're going to see this format later on, can you show that your answer here is equal to this guy down here, where there's a constant adding and e to the 2t is by itself? It's actually pretty darn easy, promise. There's only, I think, one step that we have to do, right? If we wanted to get e to the 2t by itself, then we need to remove that 1/9. And I think to do that, we can multiply by 9. And that gives us e to the 2t divided by, I'll move the e to the 2t to the front, plus 9. And there we go. We have our constant over here. All right, so let's get some background on this logistic differential equation. We're going to actually begin, though, talking about exponential growth. Now, you should remember that exponential growth and decay is something you learned in Algebra 1 and then in Algebra 2 and maybe again in pre-calculus, and now we're bringing it up again, so it certainly doesn't go away. What do those look like? Well, exponential growth is just an equation that starts at some constant and multiplies by itself multiple times. For example, if you had the equation 2 to the x and you said x was 4, that'd mean multiply 2 by itself 4 times. Then x is 5 and x is 6, and they follow the general format where they grow away from the x-axis. It is possible to grow away negatively as well, just as a heads up. Okay, and that is very similar to our decay model, where if you have an exponential decay, that is where you multiply a number by itself, but it gets smaller, not negative, but smaller. And I think that means that our base then will have to be a number less than 1, but greater than 0. And so what's going to happen is if you multiply a fraction that's less than 1 by itself, the outputs get smaller and smaller, and they grow to 0. There's an asymptote at 0. You can decay negatively as well if you'd like. Now, why are those relevant? Well, we're going to quickly talk about their growth rates. Growth rate? Oh, that sounds like a derivative, doesn't it? Well, it is. The rate of change of an exponential population, we're going to call this P, right? We see these a lot of times. They talk about bacteria where they split in half, so they continue to double themselves, so on and so forth. The rate of change of an exponential population is actually proportional or related to the value of the population. And that sounds kind of confusing, so we should probably get a quick example right here. So what does that mean? Well, it means that the equation for the rate of change, for the derivative, can be written using the original equation, though sometimes it's multiplied by a constant. So I'm actually going to show you the example and then jump back up here. For example, if your population, the amount of the thing that was there, is described by e to the 3t, then the derivative, the rate of change that describes how fast the population in this case is increasing, would be 3e to the 3t. But wouldn't it be maybe an easier way to write this if you realized that e to the 3t is the same thing as the output? And so couldn't we replace e to the 3t with the original equation? And so that's what we have over here. P prime can be written as 3 times p. And that's actually one of the characteristics that is always true about exponential growth and decay. You can always write its derivative as a constant times p, where p stands in for the original equation. Right? That's why derivatives of exponentials don't change. Right? You don't apply the power rule. They stay all the way through. If you solved an equation of this form, then you will find that they always have the same solution format, where the same solution format of any exponential is going to be e to t multiplied by a constant k, and if k is greater than 0, that is going to keep e as a number larger than 1, and so we're going to see growth. If k is less than 0, we're going to see decay. And then there's going to be some constant out front, usually as a result of that plus c of your integration. Now, what does that mean? Well, it means if you had some equation like this, and let's say that we had just dy dx equals, I don't know, some constant, let's call it 3 times the original output y. Or written a little bit more succinctly, y prime equals 3 times y. And we said, we want you to solve this differential equation. You could be able to recognize, oh wait, the derivative is written in terms of the original output. That means my answer is going to be exponential. It's a giveaway there. Now, we don't actually have to solve this, but it's just kind of showing you what's going to happen as you get to higher order or more interesting differential equations. Great. Now that we've talked a little bit about exponential growth and decay, and we'll see that a few more times, we can finally get into logistic equations or logistic functions. Now, for exponential growth, our growth is unlimited, right? The graph goes up and up and up forever. So although that's a nice model, it's not often realistic. With real populations, let's just pick the obvious one of humans on planet Earth, growth often has an upper limit. Sometimes this is called our carrying capacity, right? How many humans can the planet Earth actually carry before it can't carry any more humans? And there's all sorts of reasons why we might approach a carrying capacity. It might be a lack of resources, lack of space, a combination of the two, or other factors. However, once you hit that carrying capacity, the population can no longer be sustained and it stops growing. At that point, it might sit at the carrying capacity if we can maintain that, or if we've exhausted all of our resources, it may start to drop again. This idea or growth model is what is described by logistic differential equations. The same way that our exponential growth equation is described as a constant times the original population, our logistic growth equation is almost exactly the same. Notice this is the exponential piece, but then we have the second piece over here, this L minus P. So quickly defining some variables, T is always going to be our input over time, what's happening. P is going to be our output, how many individuals in a population. L is defined as our carrying capacity. Sometimes people will use C as carrying capacity. I don't like that as much, even though it seems obvious. You're like, C, capacity, cool. And I don't like that because we're going to be using integration a lot, and you get a plus C in integration, and then you start to confuse the letters. So I use L. And then K is our constant of proportionality. I'm going to say which is greater than 0 for now. In 99% of the cases I see K is greater than 0, but we will talk about when K is less than 0. Okay. So looking at this then, this is our exponential piece, but then we have the carrying capacity minus the overall population that does very interesting things to the solution curve. It incorporates the carrying capacity, and we'll show you how it actually helps us illustrate where the carrying capacity is and why our logistic equation can never surpass that. Now, it is sometimes written with L factored out, and we should be in our algebra careers able to do that, right? If you divide L out of both of those, you can write it like this, though the L stays, so it gets written out front. L over L is 1, P over L doesn't reduce, what stays as P over L. And so sometimes you will see our logistic growth model written this way. I heavily suggest you just memorize this first equation up here. Because if you memorize the first one and then you're like, oh wait, I need the other one because there's a 1 inside, then just divide the L out and take 5 extra seconds to do that instead of memorizing both. But if you have a lot of free time and you want to memorize both, go wild. Now, I did mention on the first page that it is possible to solve these logistic differential equations, and we actually did one. We used separation of variables, partial fraction decomposition. But as I also mentioned, that is never actually tested on the AP exam, and it will not be tested. In case you're curious, though, the solution to the logistic differential equation fits one of the two formats below, depending on how you wrote it, how you solved it, where your constant was. We made ours look like this format. However, you could also have it where the carrying capacity is up top and it's divided by 1 plus whatever's there. But you don't need to memorize these. That's just for fun facts and knowledge. You are, though, expected to memorize the shape of the graph of P of t. Luckily, though, we can actually figure out the shape of the graph without knowing the equation for P of t. And the nice part is the shape of the graph never changes. So how are we going to figure out the shape of the graph without actually graphing this? Well, we're going to use our knowledge of derivatives. That's how we've examined graphs in the past. So the first thing we're going to do is look at the logistic differential equation, this guy up here, because this is the first derivative of P. And then we're going to find the second derivative, aka P double prime. So let's move on to our next page. I've tried to go through this pretty quickly just because it's a nice introduction, so don't stress too much if you're a little bit lost on this part. We're going to make everything clear on the last page of the video, which is the next page, promise. So how do we use the first derivative to analyze a graph when we don't have the graph? Well, most commonly we find critical points. So let's take this guy and find critical points by setting our derivative equal to 0. That's what we see down here, yeah? And of course, if our derivative is set equal to 0, we have k times p times L minus p. Those are a whole bunch of factors. Now, k is a constant. K is always going to be a number that's not 0. We don't want k to be 0 because if k is 0, then it cancels out the entire thing, and because it's a constant, it's there the whole time, so now we have a growth rate of 0, and that's generally not useful or interesting to study. So we're only really going to focus on setting p equal to 0 or L minus p equal to 0, which means that either p equals 0 is a critical point, or if you add p to the other side, p equals L is a critical point. However, that's kind of strange because if we had a population of 0, well, that would probably be pretty bad because then there would be nobody there. And we also find it weird if the population equals the carrying capacity, right? We can't equal it. That's the ceiling that we're getting closer to, but we can never actually reach. So it should make sense that P is never actually going to equal either of those values. If it did equal those values, those would be critical points. But in the kind of real world perspective, we're just going to be approaching those values. It might be a bad year and our population may approach 0. It might be a really good year and our population may approach the carrying capacity. And I'm using approach, so it probably shouldn't shock you too much that what's going to happen is as we approach a time of 0, right, then our population probably approaches 0. And as we approach a time of infinitely far in the future, our population hopefully approaches the carrying capacity because we're growing up to there. If we don't approach the carrying capacity, then that probably means that we're decaying down to 0 and something bad might have happened. Now, the last thing we want to look at are the signs of the first derivative. As we mentioned above, there are 3 factors involved, right? These 3 guys. And so these factors are going to control the sign of the first derivative. We're going to continue to assume that k is greater than 0. We'll look at what happens when k is less than 0. So I think what that really is going to tell us then, if we think about the signs here, that if k is greater than 0, k is always positive. Population, that definitely needs to be positive. That would be really bad if our population was negative values. I don't know what that would mean. And then because p is always smaller than the carrying capacity, then we're doing a big number minus a small number, which means that is always positive as well. And so I think we can fairly quickly conclude that our first derivative is always positive. So since all of our factors are positive, p prime is always positive, which means that p of t is always increasing. We have a graph that is growing. But graphs that grow can have different shapes. They could grow like this. That's constantly increasing. Of course, this is also constantly increasing. And so I think in order to know a little bit more about our solution curve, we'll also need to look at the concavity. Well, before we even do anything with the concavity, we can actually look at the first derivative really quickly. And if we distribute that factor on the outside, we get KLP minus KP squared. The only variable in here is p. P. K and L are both constants. So if I rearrange this slightly, we have negative some constant times p squared plus KLP. Isn't this a parabola? In particular, because k is positive or we're making it negative, p squared always positive, isn't this a downward-facing parabola? So if our derivative is a downward-facing parabola, then what do you think that's going to suggest about our concavity? Well, the concavity is the second derivative. The second derivative will measure the slope of the first derivative. This is the first derivative, p prime. If we think about the slopes, my slopes are positive and then negative. So to me, that means that p double prime is going to be positive and then negative, or p is going to be concave up and then concave down. However, let's actually prove that hypothesis using the second derivative. So we'll take the derivative of this guy over here, right? d dt of each side to find our second derivative. K and L are just constants, so they are just hanging out. But the derivative of p is going to be dp dt, right? And then minus, the 2 comes down to kp to the first times dp dt. I see a couple common factors here. dp dt we could probably factor out. And then I also see k in each of these, which we can also factor out. And I think that's going to leave us L minus 2p. And so our second derivative reduces down pretty nicely, k times dp dt times L minus 2p. Now let's do the same thing that we did before. Let's find critical points, though these are possible inflection points, by setting the derivative equal to 0. And so we'll see those same 3 factors equal to 0. Right? Looking over here. Of course, we already know that k won't be 0, discussed that earlier, and dp dt isn't 0 either. We saw dp dt, the change in the population is always positive, so those two are out. The only potential inflection point is L minus 2p equal to 0. And through a bit of algebra, shouldn't be too awful, right? You could add 2p to one side, divide by 2. We'd find that p has a possible inflection point when it's equal to 1/2 of L. Or putting this in context, when the population equals half of the carrying capacity, the second derivative becomes 0, or p has 0 concavity. However, is that spot actually an inflection point? Because remember, an inflection point isn't where the second derivative is 0. An inflection point is where the second derivative changes sign. And it is possible that maybe we approach the spot where there's 0 concavity, and then we stay maybe concave up after. And so to view the concavity, we should probably make a quick sign chart, right? Sign chart wise, don't need to do too much here. We have our second derivative. We're going from 0 to the carrying capacity. There's a potential inflection point right here. How do we figure out what's happening? Well, we start to find values of p. So if we found a smallish value of p, and actually maybe we could even put numbers here to make this relevant. Let's say we had a carrying capacity of 50 or something like that, and we had a current population of, oh, I don't know, let's see, half of 50 is 25, so this would be 25 in my example, so let's do a current population of 10. 50 minus 2 times 10, 50 minus 20 is 30, that is positive. Let's pick a population above half the carrying capacity, let's pick like 40. 50 minus 2 times 40, 50 minus 80, that's negative 30, so we have negative. Therefore, this tells us, and I'll do the original curve in red, that our original curve is concave up until 1/2 of L, and then concave down afterwards. Because P double prime changes sign, we know that 1/2 L is an inflection point. Also, and this will come in handy probably tomorrow, don't forget that the second derivative not only discusses the concavity of P, right, my original curve P, but it also tells us characteristics of P prime, right, because the second derivative is the derivative of P prime, so it tells us how P prime changes. It tells us how the slope of our graph changes. And because P double prime is positive, that means P prime is increasing and then decreasing. So couldn't we say that 1/2 L is not only an inflection point, but it's also the spot where P prime is increasing the fastest, right? It's a relative max, and if you're maximizing the slope, it means where P prime is increasing the fastest, right? In this first interval, that's where P prime is increasing, and this second interval is where P prime is decreasing. So now that we have all this together, let's go ahead and take a look at the graphs and make sure everything we found actually makes sense. We're going to look at the growth logistic function, which is pictured over here, and we should note a few things. First, the asymptotes. They're using C as their carrying capacity, as I mentioned they might. So we have our carrying capacity up above. We also have 0 down below. Our graph never quite gets to either of those. Okay. We notice that this graph is increasing everywhere, positive slopes, right, if we drew in tangent lines, and there's an inflection point. We are concave up, and now we're concave down, and that inflection point occurs at half of the carrying capacity, right? We get halfway up to the carrying capacity inflection point, still have to go the other half. So we're getting steeper, 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 steepest. This is when our population's growing the fastest, and now our population growth starts to decrease. I did mention before that it is possible for a logistic function to decay. It's less common on the AP exam, and the only thing that causes a logistic function to decay is our constant of proportionality k, and I'm going to write this over here. K would have to be less than 0. That would cause our exponent to be negative, which would in turn turn e into a fraction 1 over e, which is now decay. Our growth is when k is greater than 0. We're actually going to look at that really quickly to finish off for today, and then we should be good. So the point I wanted to conclude with today is that a logistic differential equation actually only forms a logistic curve based on where the initial condition occurs. Right? Our initial condition better be somewhere in between the carrying capacity and 0. It would be really weird if our initial condition was above the carrying capacity or below. Very weird if it's below, because then we have negative population. Very weird if it's above, because we're supposed to be increasing to the carrying capacity and we're not going to decrease from up there. Then there'd have to be something else. So let's look at those couple graphs really quickly. I prepared them on Desmos. So here is our first instance of a logistic differential equation. You'll notice it uses that 1 minus notation, which means this stuff out front is that k times L times P, but also this guy is L. And if you're like, wait, how do you know that's L? Don't forget, way back here, the equations we asked you to memorize. If it's 1 minus something, L is always the denominator underneath P. So this is telling me then that my carrying capacity is 12. Also, and I should probably do it like this, is L. This guy is k times L times P, and we'll talk a little bit more. In this case, we're using y for P. And this is a positive value. Y is positive population, L is positive carrying capacity, and so clearly K is positive here, because if K wasn't, we'd see a negative. In fact, over here, this is going to be an example with K less than 0. So this should be a growth logistic curve. So let's look at these initial conditions, right? My first initial condition is 3. And you want to ask yourself, is 3 in between the carrying capacity of 12 and a population of 0? And yeah, it is, right? 3 is somewhere in between. So I would expect this graph to show a logistic curve. Okay, so what I'm going to have you guys do is actually sketch in the graph, but I'm going to show you the graph too, and we're going to identify a couple key pieces here. So I'm just kind of drawing this guy in over here. Doesn't have to be perfect. We could at least put the carrying capacity of 12, right? That's not bad. Something like that. So we'll call this 12. And then we could also put in the lower bound of 0. And actually that's going to be the same pretty much every single time, but I'm going to alter the graph a little bit. So let's just start with that. Okay, so what does this look like? Well, prep this on Desmos. I have the same things here. This is 12, right? We can see that. This is 0. And I'm going to turn on the initial condition of 3. We'll take a look. We can see our initial condition at a time of 0. There's a population of 3 or whatever we're measuring here. And then as we grow, we approach the asymptote and end up over here. Where should the point of inflection occur? Well, if the carrying capacity is 12, the point of inflection should occur at a population of 6, 2, 4, 6. This guy right here, and it won't be perfect, which is fine, is our point of inflection. And you can see that, right? Concave up, then concave down. Nothing bad. So I'm actually going to identify both of those on our paper really quickly. So we had the point 0, 3. And then we also know that as we go up here, my point of inflection is when y equals 6. And that's going to be our point of inflection. We don't need to be any more accurate than that. We're just kind of sketching this in just to see what happens. All right, well, let's look at the next one. Now, my initial condition is going to be 20. And so having done this a few times, I'm going to shift things around here. We're going to put that 12, which is still going to be an asymptote, down here a little bit lower. So here's 12. My initial condition is 0, 20. It's up here. And let's see what the graph looks like now. Okay, so if we flip back over, I'm going to turn this one off, flip the next one on, and there we go. We actually have an exponential decay. We're decaying down to our carrying capacity of 12. And so we can see this exponential decay that starts way up here and decays down to my asymptote. Well, I bet you can guess what happens then with y of 0 equals -5, or maybe you can't. So we're going to go ahead and kind of move our axis up here. We don't need 12 anymore. Now the bound is going to be 0. We do need the initial condition of 0, -5. And let's take a look at that graph. Okay, if we put that below our 2 bounds, now we are growing away. So it's actually interesting. One of our initial conditions causes exponential decay. One of them causes logistic growth, and the other causes exponential growth. It's kind of weird to think of this as growth, but we are growing infinitely negative, I guess. And so we're getting bigger and bigger and bigger, just in a negative direction. And so if we sketch this in, this will give us our graph that started at the asymptote and decays away from there. Okay. Let's do the same thing. We'll do this one a little bit faster. I'm just going to show you all 3 graphs and then you can sketch them in. But now let's see how this logistic growth differs when k is less than 0. This is going to be logistic decay. I am going to sketch pretty much the exact same graphs, or at least the same axes, and then we can change that when we get back here. So we have this guy, this one, because all the initial conditions are the same. The only thing I changed is I gave a negative value of k. And so this guy at the end is going to be up here. There we go. We have the same points, something like this, something like this. We have the same asymptotes. I didn't change anything else besides make k negative. It's going to be 12 over here. This is going to be 0. There we go. All right, so we're just going to click through all 3 pretty quickly, fill in the graphs, and that's all we're covering for today. So let's save this one, pull up my other one, k less than 0, there we go. So we have the same bounds here. Let's look at our first one. 3 is in between the carrying capacity and 0. This should be some sort of logistic model. And if I graph the curve, it is, but it is logistic decay this time. You'll notice the inflection point still happens at a y value of 6 over here, just with negative time. And that does happen depending on when you start observing, right? I start observing here, and we decay after that, but it is still logistic decay. My next one, now it shouldn't surprise you, it's the opposite. Now we are growing exponentially, and for our last one, we are decaying to 0 at the end. So quickly sketching in these 3 graphs, we have logistic decay for the first one, wrong color, logistic decay which comes down here, and we have our inflection point. Okay. You'll notice that I didn't identify the inflection points over here because for these two, they don't have any inflection points. They're concave up or concave down everywhere. They don't shift that inflection. This guy was exponential growth this time, and this one was exponential decay. And there we go. So again, we are looking at a family of differential equations known as logistic differential equations. They only become logistic or form a logistic curve when our initial condition is between the carrying capacity and 0. If we want to find the point of inflection, right, we go through and we just take half of the carrying capacity. We need to realize that if k is greater than 0, our logistic curve increases everywhere. If k is less than 0, we decrease everywhere. And that's really about it. You don't need to do too much with these. So when you come back next class, so tomorrow or whenever you get back to this, we'll look at some actual examples, and then you guys will get some time to practice. So thank you as always for tuning in. I'm excited for one more day of learning, and then you guys get to really start prepping for that AP exam.